Welcome everybody to the webinar today. This is our second webinar of the year, so we're going to continue to have these throughout the year. I'm going to pass control over to John here, and we're going to get going on this thing.
All right. You know, before I get going, I'm going to tell you another story. Before I got into energy efficiency, I used to do sound and lights for theater, but mostly for dance. And I worked in San Francisco and Minneapolis, but mostly San Francisco. And I remember once I was working a show for maybe some of you, if any of you are dance fans. I mean, you're engineers, so maybe not. But if you're dance fans, you might have heard of Alonzo King's Lines Dance Company. It's a ballet company. They were really good, and they were based in San Francisco, and they're still around. Anyway, I remember I was backstage, or actually on the side of the stage. They call it the wing. So I was on the side of the stage, and this ballerina was dancing along with a man. I don't know what they call the male ballet dancers, but he was, you know, holding her, and she was spinning and doing pirouettes and doing all the beautiful things that they do. And I mean, ballet is beautiful when it's well done. And the woman, you know, was traditional ballet, you know, uniform with the leotards and the little skirt and the makeup, you know, the red lipstick and the red cheeks and everything, you know, and just looking beautiful and you know, falling into the guy's arms like a rag doll, you know, the way ballerinas do that, and just so, you know, their arms moving so beautifully and all of that. And it was beautiful to watch, at least for the audience. And then she runs off stage, and I think that the male, I don't know what he did. He might have ran off the other side, because I only saw the woman run off, and she ran off towards me. And then all these other ballerinas come on, they do some group ensemble thing. And when she was off stage, I saw her close up, and she was totally bathed in sweat. And under her underarms, there was like 8 inches, a pool of sweat, 8 inches under each underarm. She was totally drenched in sweat. But that wasn't it. She was like leaning against the wall, and she was breathing like a horse who'd been galloping for an hour. And she was breathing like this. Excuse me, she didn't cough, she was just breathing. And I thought, wow, that is amazing, because she looked so unattractive. She wasn't beautiful like ballet dancers are on stage. It was like a horse who was getting ready to die. And then her cue came. She stood up straight. She put on that beautiful ballet smile and scampered back out on stage and started doing her pirouettes and all that other stuff again. And I thought, wow, that is really neat. The big juxtaposition between what is real and what you see. They're really different. And they're only different for people who don't know ballet, the people who don't know what goes on behind the scenes. Now, people like me who've been behind the scenes, we know. And so when we see some other dance show, you know, and we see them, all this stuff going on, we also know or can imagine what's going on behind the scenes, you know, when the ballerina runs off stage. Anyway, I thought that was interesting, and it actually has something to do with what we're talking about. We're talking about utility bills, which, if you ask me, when I talk to lay people, it's like the boringest topic in the world. But it's this talk that I'm going to give here is actually really interesting, and this might be the most interesting talk I ever give. And it's interesting because, again, it's just like the ballet dancer. You know, you can take a look at these bills, and you will, and they're nothing at all. The reality is nothing at all like they appear. And I know that doesn't make any sense, but it will in a moment. And if you have just a little more knowledge, then you can see the reality. And this knowledge you're going to have, I don't know, 25 minutes from now. So let's get going. Okay, so this is an outline. I'm going to give you a handful of fabulous examples. And it basically, I'm going to show you data without weather and then with weather. So the weather is really the secret element here. And then we're going to look at balance point, and we're going to look at load factor. Okay, so it's 3 things. So first, here it is. This is real data. As you can see, it's old, but it's from a retail store in Bay City, Michigan. So we have January in the middle here. It looks like in the summer, July and June are on the edges. So it looks like they use more energy in July in June. So summer they use more, and they use less in the winter. So me looking at this graph, I would say this isn't very clear, but I would say, there's not a lot of weather variation, but it sure does look like they're doing some cooling with this electricity. That's all I can really tell you. Now what I'm going to do is I'm going to apply weather data. This is a screen from Metrics. I'm sure almost every one of you has seen a screen like this before. It's just the high and low temperatures for every day, okay? And what we're going to do is we're going to, well, I have a graph right here. Actually, this is the same data. So each one of these points is one of those bills that I saw 2 slides ago. But on the x-axis, what you see is the average temperature for each bill. So basically, we took the high and low values for the billing period, averaged them all up. It's such a gross estimation, but it works. And we graph this. So the x-axis, again, is the average temperature during the bill period. That is the average of all the highs and lows. And then the y-axis is just usage per day. Okay, so what do I see here? Well, I see exactly what I saw before. I see that they were in cooling, so they used electricity to cool. I got that. There wasn't a lot of weather sensitivity. I got that. But I did not see that outlier. I did not see that. So, oh yeah, here it is. See? So constant usage in winter, that's kind of constant. Electricity used to cool, yes, but that outlier, totally missed it. Let's look at that data again. There it is. Didn't see it, totally missed it. Okay, that's kind of neat, right? So if you looked at this data, I don't know, maybe you're a lot more intuitive, a lot more intelligent than I am, and we have up to 100 people here, so there's certainly plenty of you who are, but I didn't see that. So let's just assume I'm average. That means half of us did not see that. So I think that's pretty darn cool. Let's take it further. Here's another one. Now, if you've been in my class, you might recognize this, but maybe not, you probably forgot. This is another retail store. Let's look at it again. So again, I have July and June. The summer seems to be at the edge. And I've done a ton of retail stores. And if you do retail stores, you'll see there's this huge bump. It's either November, December, or December, January, where there's this huge increase in electricity usage. And that's usually shopping. And then it looks like we have, it looks like a bump for a little bit, maybe for cooling, but maybe not, because I don't know. Because it looks like here we have cooling here, but then this one in March is about the same. So maybe there's cooling too. So, but we look at it versus weather, this is what we see. This makes it very clear, okay? It's very clear. As the temperature goes down, they use more. So it is in heat. They do use electricity for heating. But I was thinking before they were using it for Christmas shopping. No, it was for heating. And you can see how damn clear that is. So there's my 2 lines, okay? Very, very clear. It wasn't so clear before. So before I thought it was Christmas shopping. No, it's heating. So I learned something. I mean, it seems so dang simple, but then again, when you think about ballet, that's simple too. People are out there expending all these calories. Of course they're exhausted when they go on the sidelines. Of course they're sweating and breathing like a horse. It's the same here. Very simple concept, but it actually is really important. Why do people use weather? So utility bills, I guess what I've showed you so far, I'm going to show you more, but utility bills are only half the story. You need weather data to really understand what's going on. That's the point of what I'm really trying to show you here. So, when you're doing, let's say, so a lot of you people are M&V people, but some of you are involved in energy audits as well. And I think it's really important to put your utility bills into metrics and to look at that outdoor temperature graph before you do the audit, actually. And then you'll understand, how is this building using energy? You'll have a clue. A lot better than if you just looked at the usage per month, like most people do. This is a graph just like the other ones we saw, average temperature versus usage. And here's another one. So the one on the left, the first one I showed, you can see as the temperature goes up, they use more energy. So that's telling me electricity is used to cool. And the one on the left, as temperature goes down, they use more. As temperature goes up, they use more. So that's heating and cooling. And that's exactly the same graph you saw earlier. It's just a little compressed. When we do this metrics, tuning, one of the things we do is we estimate the balance point, and we do it with this same graph, the outdoor temperature graph. So what we do, I teach this in intro class, we just imagine a horizontal line that goes through a portion of the bills, just like that. And then we imagine another line that's going through the bills that slant up to the right or to the left. Okay, where these two lines intersect, that's what we call the balance point. And that's the temperature at which the building starts to cool. Okay, so right here, this building starts cooling at 56 degrees, maybe 56.5 degrees. So that's kind of cold, right? Now, when I say cool, that doesn't mean that they're bringing in outside air. No, it means mechanically cool. It means that they're turning on their heat pumps or their air conditioning units, or this was a school, so it might be that. It might not be a chiller, but they're turning on the cooling equipment at 56 degrees. Now, it would be a lot better if they just opened their windows, or if they if their economizers worked in their buildings. 56 degrees. So, it's 57 degrees and they're using mechanical cooling. It doesn't make sense, right? So that's what, by just looking at this balance point, you can identify whether or not there are problems with the economizers, or if they're getting enough outside air. Now, there's a lot of buildings, especially like in Texas, where they don't bring in a lot of outside air. That's just not part of the deal, because of, and maybe it's all the Southeast, because there's so much humidity, they don't want that. But so sometimes it's just it's kind of, what do I say, the ducting and the structure of the building will limit it, and you'll always have a low balance point like this. But in a lot of buildings in a lot of parts of the country, you could have 100% outside air, and you don't need to have a balance point of 55. Oh, here's the same thing with gas. So I'm gonna go through that same old exercise where we have, I imagined a horizontal line, and I imagined a line that's slanting, in this case, up to the left. All right, so where these two intersect, that's my balance point. Here it is 67. That's the temperature at which the building starts to heat. That means at any temperature below 67, we're in heating. Okay, so good. Okay, so once we know a balance point, the next part is we calculate degree days. Degree days is basically the average outside temperature for each day minus the balance point that we just figured out, okay? So we do this for each day. That is where the outside temperature is the average between the high and low temperature for the day. So remember I showed you that metrics chart of the highs and lows? Well, you just average the two of those. That's what the average temperature, that's how we're defining it. And balance point temperature is the balance point that we found earlier in that last graph, okay? You can't have negative cooling degree days for a day. It's just, by definition, they don't allow that. And then what we do is we sum them up for a billing period, okay? So we sum up all the degree days for a billing period, and that's the number of cooling degree days. And it's the same for heating degree days. I'm not gonna read this one, and please don't read it, but it's the only thing we changed is these two are switched around, okay? Do you need to memorize that? No. Okay, so once you have these degree days, that's what's here, degree days per day, kilowatt hours per day, and then we do these regressions, right? We've seen this in metrics, everybody's seen it. These are your statistical indicators and all of that, but here's the balance point. And again, I mentioned the balance point before, and here is, I don't know what this meter is, but this one starts cooling at 46. So we're bringing in, wow, we're doing mechanical cooling at 46. You could be doing outside air. You don't need to be doing mechanical cooling. So if you looked at this data before an audit, you know to look at an economizer. Another aside. Something I heard someone say at a conference, and it was hilarious but true, and that is the whole concept of economizers. If you've done enough auditing and retro commissioning, and actually it doesn't take a lot, you know that they never work. You can go to any building and you know there will be economizers that are not working. That's just the way it is. In fact, it seems to me, or at least it seemed to him, and I'm taking his thought, that economizers actually waste more energy then they save, because they never work and they bring in outside air at the wrong times. I thought that was really fascinating. But so maybe you don't need to look at utility bills to figure out the economizers aren't working. Maybe you should just assume that they aren't working, because they never do. Let's look at more of these. This is retail in Florida. Actually, this time, so you know the drill. We look at this monthly data, and then you think, okay, so what does this mean? How would I interpret this? Well, this one's a little different because January is here, okay? So that's December. So I'm pausing so you can actually think, okay, this is what I see. I think this meter tells me this, and this meter tells me this, just from looking at this. I'm stopping. Okay, that's it for thinking time. This is what I saw. Electricity is used to cool. I bet you saw that. Okay. And electricity is used to heat. I think so. So we got January and December. Electricity is used to heat. Okay. It's Florida. Maybe in November it's not that cold, and in February also. I'm not from Florida, but maybe that's how it works over there. That is what the data looks like. Didn't see that at all. So what is this? What are we looking at? What we have is, these are the first 6 bills, and then it changed. There was a change in usage pattern, and here's the next 6 bills. Okay, that's the data. So then now that you see that, you can see, oh yeah, it does shift down. Okay, I can see that. See, now you can see it, but you couldn't see it before. Maybe, you know, some of you did. Yeah, pretty cool, huh? One thing you can see from this, so the first line, the one at the top, that is what they used to use. The one at the bottom is what they use now. So what you can see from this is the slopes are, I think they're about the same, okay? So if the slopes are the same, I mean, first off, let me back up. The first thing we can identify is what month did they make a change in usage pattern. We can identify that. That's pretty darn easy, because we'll just go back to this slide and say, oh, it's the last 6 months. It's that one. So they made a change somewhere in between this and this billing period, somewhere in there. So that part we know. But the next question is, what kind of change did they make? Well, we can actually identify that because we can see that these slopes are, let's pretend, parallel. So if they're parallel slopes, that means that the change they made only affects what we call base load. In other words, it's the non-temperature sensitive usage that changed. But the temperature sensitive usage is the same because the slopes are the same. Okay, so here's the same data. So here I tuned one of them, and I wonder if I think I have the same balance point for both. So I don't remember if I do or not. I'm hoping I do. But you can see that they look pretty parallel, right? But the big change is the usage per day. I see the cooling degree days changes too. But basically what we can see is the slopes are not changing much. It is the base load that's changing. And that's telling me that the type of change that they made in this building is probably something like exterior lighting. That would be my first guess, exterior lighting. If not that, then my second guess is lighting interior, which I don't want to guess, but it could have been that. My guess is it's something that does not affect cooling usage. Okay, that's why I said exterior lighting. The thing about interior lighting is it does affect cooling usage a bit, and that should change the slope just a little bit. So because the more efficient LED lights, they produce less heat, and therefore there's less of a cooling load, and then the chillers run less. So so lighting retrofit should actually change the slope a little. But what I'm trying to point out in this whole demonstration of this retail in Florida is that you can identify changes in usage patterns, and you can identify the type of change. Did the slope change, or did the base load change, or did both change? And when they do, then you're left with a set of guesses. It could be this, or this, but at least you know something. And you can go back to the building and say, what happened? What happened? And then they can give you an answer, and you can decide if it was a good idea or not. Okay, so that's it for the section on balance points and weather. Next topic is load factor. This is kind of cool. Actually it's really neat. And some of you already know this trick, but that's okay. I'm going to show it to you anyway, I guess. This is real data. They're high schools, actually where I live in Central California. I just changed all the names. So we're looking at load factor percentage over a couple years. And load factor is calculated this way. It's a measure of demand relative to usage. And basically load factor can tell you how the building's using energy. Let me explain that. So it's what we're doing with load factor is we take average kilowatts over actual. Now actual kilowatt, what I mean by that, that's metered. That's metered kilowatts, okay? Average kilowatts is a different concept. And what average is it's you take the total kilowatt hours and you divide by the number of hours in the bill. Okay, so how many days in the bill? There's, let's say 25 days times 24 hours, and you end up with some number. And yeah, and you end up with the average kilowatts. So that's like the equivalent of if you just turn something on for the entire billing period, you know, at what demand level do I have to be at to get the amount of kilowatt hours we used in the building? What would be my average demand? That's what this average kilowatts is. Okay, so load factor is average kilowatts over actual kilowatts, and here I actually did the equation right. Okay, now, so that's all the equation stuff. So let's see what this looks like now. I made this little chart. It's kind of cool. So if you have a really high load factor, it usually, like 95% or higher, it usually means you got a billing error. That's what it means. You cannot theoretically have one greater than 100%. If you look at your Gulf Med project, if you have metrics, which I think almost everyone here does, and you open up Gulf Med, which is in the metrics data directory, and you run a bill ledger report, you'll see that there are load factors greater than 100%. That is theoretically impossible, which means that there's a metering error, okay, or billing error, but it's probably a metering error, okay? If you have a really low load factor, it probably is also a metering or billing error, okay? Now, these other two, we're gonna talk about these in a minute. I came up with some, let's say, average, how do I explain this? I took, you know, 30 hours times 24 hours per day and put in different, you know, percentages of load and came up with these graphs. So a load factor of 60% looks like this in general, where, you know, on weekends, you know, during off hours, it's half of the power is running. And they run, you know, the building, most of the building is open or part of the building's open. And on weekdays, yeah, they use a lot. And then they turn off half the building when on off hours. Okay, so this to me looks like a hospital, okay? So if you look at hospitals, they should have load factors around 60%. That's what this looks like, okay? They might be 50, they might be 70, but they're gonna be around 60, okay? Now, what this means is if you see a load factor around 60 and you are someone that's looking to save energy, then what you might wanna do is see if you can turn stuff off. So you wanna reduce these ones, okay? Because it's just, so we haven't even been to the building. We just looked at the bills, but we can see just from looking at the load factor, oh, it's around 60. They're not turning things off. So you know before you get to the building, oh, I'm gonna look for things that I can turn off. It's just, that's what load factor analysis lets you do. Here is a load factor of 30. So let's say, you know, they use a lot during the days, weekdays, and then they turn it off or they bring it down to 10%. So a little bit runs at night. And then on weekends, nothing runs either. Okay, so that would be a school. So you'll see schools are around 30%. Okay. Now the best way to reduce energy here is you need to reduce this because that's where it seems like the greatest opportunity is. Okay, so that's a load factor of 30. Okay, so let's look at 95. That's the one I said was a billing error. That means that they're pretty much using about the same energy draw or demand every hour during the billing period. That's what that means. Okay, that doesn't happen very often. It just doesn't happen unless maybe you have street lights that never turn off. But yeah, that looks like a billing error to me. Okay. and here's one that's 5%. So they use a certain amount of energy, and then they have this big spike once. No, this is a spike that happens every day, I guess. But that's what you've got. But this is what a 5% looks like. It doesn't happen. You're not going to see these, or if you do, I think you should assume that there's a problem. Okay, so let's look at this graph here. These are those schools again, and here I have one really high load factor. So that's my billing error. Yes. Here I have, why is my purple line higher than all the rest? Well, my guess is that, so these are schools. Remember I said schools are around 30%. This is the really efficient schools. They turn everything off. But here, I think that this one, they're not turning stuff off, obviously. Why? I don't know. I don't know. They're just not turning stuff off. That's all I can say. Maybe on weekends, they're not turning stuff off. So if I was doing an audit of all these buildings, that's one I would look at and find out why. This one's interesting. So the green one, it was like all the other schools, and all of a sudden they had a much higher load factor all of a sudden. My guess, I don't know. I just made this up. I'm an imaginative person. I assume that they got a new janitor and they don't turn lights off anymore. That was my guess, but you know, who knows? I really don't know the answer. So this is my summary. So there's really clever and I guess that it should be clever and easy ways to analyze utility bills to determine what's going on with the building. It's so easy. You just put them in the metrics and look at the weather graph. That's it. So with weather, you can identify changes in usage patterns. We saw that. Building balance points, whether the meter is heating, cooling, or both. And with load factor analysis, you can determine whether the building's shutting off the equipment, you know, at night or weekends. And you can also identify some problematic bills or meters.
We have some time for questions. Hopefully this time everybody is typing their questions in the response box. Let me look. I don't see any currently.
You guys, one thing I forgot to tell you, and that is you're going to get an email probably tomorrow. We've just finished, finally, gosh, it's taken like 5 years. It's a joke how long it's taken, but we finished our new software. It's called Option C. It's like metrics right now, actually. And it is, well, let me explain why we did it. So some of you who've been using metrics for a while, especially those of you using for a long while, you know that there's only like 244 rows in any field, and that can get maddening if you've got a 20-year project, because it is really a pain in the neck to measure bills on the 21st, 22nd, and whatever years, because now you've got to take away a year or two, and it's really awful. And I know it, and I apologize. There's a couple other drawbacks of metrics. I love metrics, by the way. I love Excel more, but I do love metrics. But there's drawbacks with everything. And another drawback of metrics is that when projects get too big, they get slow. That's awful for people with really big projects. Now there's workarounds like break it up into several projects, and you can always have Report Maker, just open all the projects at once. That's all true. But still, Report Maker might run slow if you've got 200 meters in your project. So that is another, let's say, drawback of metrics, which unfortunately, neither of those two drawbacks we can fix easily. They basically have been told, you got to rewrite the darn software if you want to fix that. And it was because of some database decisions that were made in 1994, 95, by SRC systems years ago. So, but that's bad. So it's awful, actually. So, and the third drawback is, again, let's say every strength that we all have individually is also a weakness. If you're a super honest person, then when sometimes that honesty can get you in trouble. When someone says, well, how do you like my painting? And you say, oh my God, that's the worst piece of puke I've ever seen. Your honesty really didn't do you any good there. And it's the same with metrics. One of the great benefits or great things about metrics is the Excel reporting, or I think it's great because you can do anything because Excel is the best program in the world. But the bad thing about metrics having Excel reporting is that, well, Excel keeps changing. They keep changing libraries, and then there's 64-bit Excel, which doesn't work with Metrics Report Maker, and all these little problems like that, and they keep coming up. And if you've been a metrics user for 10 or 15 years, you know that, I mean, you've probably already run into one problem and had to deal with tech support to get around it. It's a pain. It's awful, and I know it. And so, but at the same time, Excel reporting is wonderful. So option C doesn't have any of those problems. We have a SQL database, which means we can handle all the rows. It means we can handle big projects, and we don't have Excel reporting, which is good and bad. Okay, so right now what option C has is it's pretty much just like metrics at this moment. It's got a few things that are better in its design. For example, in metrics, when you do a rate, let's say you're doing a school district, you have 200 meters, 200 electric meters, and you want to change the rate and your modeling rates, you have to drag it down 199 times. What a pain in the butt. Well, with option C, you only model the rate once and you don't drag it down. You only make a change in one rate. That's kind of nice. It's the same with variables. With variables, you can attach the variable to the project. You don't have to attach it to each area. That's nice. Or you can attach it to an area or to a site. You can attach it to whatever you want. So that's nice also. And so it's rates, variables, and weather also you can attach to the project. I think you can attach it to the project. No, I'm not sure about that. I think weather only attaches to sites, but you only enter it once. And then in the site forms, it asks what weather are you using. So that's what is different. Now, the ways that option C is, let's say, not as good as metrics at this point is that the rate engine right now is really rudimentary. It's really basic. I have a guy right now working on a rate engine that will be much better than metrics' rate engine, and that should be done, my guess is I'm hoping by June or July. So that's coming, but basically, let's see, I told you what it does. We also have a converter that converts metrics projects to option C projects, so that's not a big deal. But I want to tell you a little bit about, that's another one of those taps, I'm sorry. I want to tell you about the changes that we have in mind, actually not in mind, that we've already written the specs for, and Kirill is starting on them. Actually, he'll probably start in a week. And that is, we're going to add this capability to two regressions. So you can do one for pre-retrofit, just like you're doing now, but you can do one for post-retrofit also. And the idea is you have two of these regressions, and then you apply TMY data to both. Okay. One of the drawbacks of this method of M&V, and some of you, not many, but some of you run into it is, let's say you do a boiler retrofit and you got a normal year, you do your regression, everything looks good, and then you end up with a year where it wasn't cold. It was a really warm winter. So what's your savings? Well, your baseline is really low, your actual usage is low, and your savings is low. And you kind of got creamed. I mean, you weather normalized, but you got creamed. And so one way to handle this is to actually apply TMY data. And so that's, but the bad news about the TMY data is that you end up with, you might have to wait a whole year before you can do a savings report. And I don't know if you guys want to do that. But it's another way of using regressions and using utility bills to do M&V, okay? Another thing we're going to add is we're going to automate the getting weather data into metrics. So that's one thing we want to do, or not in the metrics, in option C. We might do it in the metrics, but certainly will be in the option C. Another thing we're going to do is add an interface that will take interval data, it's green button data, and it will aggregate it into daily, weekly, or monthly amounts, and then put that into option C. So that is coming as well. And then there's also a persistence module, which I'm not going to describe that in detail, but that one's coming down the road. So at least a year from now, but that one is going to actually be, basically you come up with a regression after your retrofit, and then we're going to compare to that regression, and we're going to see very quickly with daily data if your project is starting to go south. If it's going south, you'll know within a week. rather than having to wait 2 or 3 months. So that's really useful, but that's another one that's coming with option C. I think I've covered most of the things that are coming, what it exists, what it does, and all this. Now, one question.
I think one of the big questions, John, that you might have just been getting ready to touch base on it is I got a couple people that are probably asking how much does it cost?
Oh, yeah, I see that right now.
That number.
Oh, hey, Karen, I see you wrote an email. You wrote a question too. I'm going to answer that in a minute. Let's go to costing. I'll talk about in a minute. But first, I want to talk about metrics 4. We're not phasing out metrics 4. Like, for example, some companies, I just talked to one guy at one ESCO, he might even be here, I doubt it though. But, one company I know, they need Excel reporting, and they're not leaving metrics 4. And we're continuing to make, let's say, advancements to metrics 4 or make changes and keep putting out a new version. So don't be in any fear that metrics 4 is going away anytime soon, because that's not our plan, not at all. But what we want to do is we want to fix the problems we had with metrics 4, and what we also wanted to do was we wanted to add these new ways of doing M&V and these new analysis things you can do with utility bills. Okay, so I have costing. We don't really know. We don't know how we're going to cost this. I wrote up a whole costing plan, and then I came up with a better idea. And so what I'm doing right now is I'm talking to some folks at ESCOs, and basically I haven't called most of you. Like, one of the people I'm going to call, Karen, man, I'm calling you, and I'm going to call some other folks and talk to them about what I'm thinking of doing for pricing, and I want to get their input, because we want to change the whole concept of how we work with you. In the past, what it's been is we sell you software, we sell you weather, we sell you trainings, and we're always selling you something. I don't want to be a vendor anymore. What I want to be is your partner. I want to be like your mentor or yes, some of you guys know more than I do, but what we want to be is the company that helps you, gives you everything you need, the tools, the weather, the training, everything you need to make you world class at what you do. That's the idea. We want to make you great. And so that involves changing the entire way that we try to do this. Like, a lot of you haven't been to training because it costs money and your bosses won't approve it. Well, we're gonna have to find a way around that. And that's what we're talking about. So now I'm gonna answer some questions. Software to calculate load factor. Yes, Alok Kumar. Yes, metrics does it. The report maker will do that. If you do the bill ledger report, it will calculate load factor automatically. If you do any report, like a time across report, any time across report, you can select under ratios. So you can select costs, you can select, I think it's units like consumption and stuff, you can select emissions or ratios. And under ratios is load factor. So you can do, a time across items, a time across years, a time across scenarios, and those could have load factor in them. So I hope I answered that one. And let's see. Joel says, maybe charge more for a license per year, which includes Abraxas service support. Joel, that's exactly what I'm talking about. That's exactly what I want.
I think he figured it out.
So this is the idea. I'm not supposed to say this to you guys because I wanted to first, but I'm going to do it anyway. I mean, maybe I'm being stupid, but that's the way I work. So, what I want to do is we want to just hold trainings around the country, and anyone can go. That's what I want. If it's near you, then just show up. If you only can come the first day, then only come the first day. I don't care. But we have these trainings because there's a lot of folks from some of these ESCOs and also some of the school districts, et cetera. They can't go to the trainings because their bosses won't approve it. Well, guess what? If that fee is in maintenance, then I guess they can go to any training they want. It's free. So that's what we're talking about. So, but I want to talk with some folks first and see if this is going to fly. I don't want to just impose this on you and find everybody hates this idea. So.
Thanks, guys. We hope you join us on the next one, June 14th. And then we'll send the additional webinar schedule out as soon as we have that.
Thanks, everyone.
Thank you, guys.